Thanks very much. It is my great honor to have the opportunity to present my research. In this talk, I will present our solution to a very important but non-neglected problem, the extensional scalability problem. That is, in face so many software bugs, how we efficiently check them together. This talk has 4 parts: the background, the approach, the evaluation, and a brief summary. Although many bug detectors have been developed and we already have many achievements, we still suffer from many software bugs in our everyday life. These bugs may be caused by invalid use of memory, such as double-free, user-free bugs, the null point dereference bugs. These bugs also include many taint issues, such as sequence injection, command injection, and so on. We call these software bugs value flow problems. Generally, we say the value of a variable x flows to the variable y if x is assigned to y directly through an assignment or indirectly via some point operations. A value flow problem means that a value improperly flows to some sensitive program statements. Here is an example where a null pointer flows to a dereference statement through 2 variables, p and q, causing a null point dereference bug. So to perform a value flow analysis to detect value flow problems, we need to firstly build a precise value flow graph based on a precise point analysis. This technique is published in PLDI 2018. With a precise state dependence graph or value flow graph, the next step is to search invalid value flows on the state dependence graph with the help of an SMT solver to solve path conditions and prune infeasible paths. The problem we address in this paper is how to efficiently check multiple bugs at the same time. And in the next talk, I will present our technique on how to improve the parallelism over existing parallel designs. We will also present our approach to fast SMT solving in ISTA this year. In an industry setting, static analyzers often need to check many problems at the same time, which will be very time and memory consuming because more program states need to explore and there will be more computational redundancy. And the main problem is that the analysis logic of checking different problems are independently between each other, which leads to redundant graph traversals on the state dependence graph and unnecessary invocations of the expensive SMT solver. So our work is an interproperty-aware analysis, which uses the analysis results of checking one problem to speed up the analysis of other problems. The basic idea is to utilize the mutual synergy among different value flow problems to reduce unnecessary graph traversals and SMT solving. We observe that the mutual synergy among different value flow problems are mainly in the forms of path overlapping and path contradiction. For path overlapping, let us look at the example. We aim to detect the memory leak bugs and free global variable bugs on the state dependence graph on the right. To detect the memory leak bug, we need to search paths from a heap pointer to free statements. To detect the free global variable bugs, we need to search paths from a global variable to a free statement. Assume that we first check the memory leak bug by searching paths from the heap pointer A. During the graph traversal, we record the information that the vertex C cannot reach any free statement. We use this information to speed up the analysis of free global variable bugs. When checking the free global variable bug from the vertex B, we can directly stop the graph traversal at the vertex C because we have known that C cannot reach any free statement. This is an example of path contradiction where we attempt to check memory leak bugs and null point dereference bugs on the graph. For both bugs, we need to search paths from the vertex A because A is the return value of the function malloc. The function may return a heap pointer when it succeeds allocating a memory space or a null pointer when it fails. We use the condition A is not equal to 0 to represent the heap pointer and A is equal to 0 to represent the null pointer. During the path traversal, we need to check whether the path condition conflicts with these bug-specific conditions. For instance, when traverse the graph for checking the null point reference bug at the vertex B, we will use an SMD solver to check whether the path condition gamma conflicts with the null condition. Assume that the path condition gamma is satisfiable but conflicts with the null point condition. According to this information, when checking memory leak bug by searching paths from the vertex A, we can directly determine the path condition gamma doesn't conflict with the hit point condition without invoking the expensive SMT solver. This is the workflow of our approach. The input is the specification of the value flow problems to check. Each specification mainly consists of 3 parts: the source vertices, the sink vertices that determine what kind of value flow paths we need to search on the dead dependence graph, as well as the specific conditions each bug type needs to satisfy. With the specifications, we make optimization plans so that the subsequent graph traversal engine can utilize the mutual synergy for sharing and pruning paths for detecting different value flow problems. In the evaluation, we use 22 programs from the standard spec benchmark suite and GitHub. The sizes of the programs range from a few thousand lines of code to 2 million lines of code. We compare the time and the memory cost of our approach, catapult, with 3 industrial strength tools: Pinpoint, a value flow analyzer where catapult is built on, Clang and Infer are powered by LLVM and Festo. Due to the time limit, we only discuss the results of comparing to Pinpoint in this talk. The figure on the left illustrates the results of the comparing our new approach to Pinpoint. The x-axis is a benchmark program ordered by their sizes, and the y-axis is the time and the memory cost. The black lines are the time and the memory cost of Pinpoint, and the red lines are the cost of the new approach. Compared to Pinpoint, the new approach is 8 times faster, but only consumes 1/7 memory. Sometimes Pinpoint exhausts all 200 GB of memory and raises an auto memory exception. In comparison, the new approach never exhausts the memory. We also draw the growing curves of the memory and time cost against the number of value flow problems to check. We observe that the time and the memory cost grow much slower than Pinpoint, so we believe the new approach is more scalable with regard of the number of value flow problems to check. As a brief summary, to address the extensional scalability problem, we propose an interproperty-aware analysis that uses mutual synergy among different bug types to accelerate bug finding. So that's all. Thank you very much.